Hey everybody, let's check out this one from 2000, I think it is, 2001 maybe. It's a good graphing one, a good Unit 1 problem here. So we got this cart on a horizontal track. We got a velocity versus time graph here. And the first thing they want is indicate every time for which the cart is at rest. Well, this is the velocity, so 0 velocity or at rest is right along the x-axis. So that means right here and right here. So basically at 4 seconds and also there at 18 seconds are the two times in which we are at rest. All right, next thing they say, and I'm just going to do it on here as opposed to the other paper, it says indicate every time interval for which the magnitude of the velocity is increasing. So the magnitude, we don't care if it's positive or negative. Well, we're speeding up, our velocity is increasing when we're moving away from this 0 velocity. So one period that the velocity is increasing is from here to here. And then here we're slowing down, we're approaching 0. And then another place here where we're moving away from 0 is from here to here. And so this section right here is also increasing in speed. And so then if we look at writing these down actually, and I look at the graph right here, I can see from 4 to 9 seconds it is. That's one period. So 4 to 9 seconds. And then if I look here, that is 18 to 20 is the other area in which we are increasing the magnitude of our speed. All right, now let's look at the next question here. It says determine the horizontal position x of the cart at 9 seconds if the cart is located at x equals 2 meters at time t equals 0. That's a little annoying. They give us an initial position. You can just find a normal displacement and add 2 on it at the end, or you can call that the initial position. So let's do that. Think about what we know. We know that the time is 9 seconds. We know that our initial position is 2 meters. And let's look at the graph and see what else we can get. One thing is we can see that this whole time here, by the way, we can do this in one step because this is all one constant slope, so one acceleration, and so we can do it in one equation. We can see the initial velocity is 0.8 meters per second, so I can write that down. We can see right here that the final velocity is -1 meters per second. And another thing you can do is you could calculate the slope of this graph because that would be the acceleration. And I can see here that every second we go over, we drop 0.2 meters per second in speed. So our acceleration is -0.2 meters per second squared. The fact that we know 1, 2, 3, 4 things here, that lets us give, or that gives us a choice of equations to use. I'm going to use the third one. It just seems like we're so familiar with that one. That says the position is the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. Starting to plug in for there, my initial position is 2. My initial velocity is 0.8 meters per second. We travel for 9 seconds. And then my acceleration is -0.2 meters per second squared. And my time again is 9. And don't forget to square that. So we start to solve this. We get 2 plus 7.2 minus 8.1 there. And then so we clean all this up. Our final position is going to be 9.2 minus 8.1, so 1.1 meters. You could also have used the fifth equation since we know the initial and final velocities, and we could solve for the displacement and add that onto 2 meters. You actually have a lot of choices of which way you could go there. All right, so now let's go on to this one where they say help us find the acceleration or graph the acceleration from our other graph. So what we're basically doing is we're graphing the slopes of this graph. So from 0 to 9 seconds, we have that slope that we already found, which was -0.2. And so from here out to here, we've already got the slope. We can then find it for this section right here, and if you work it out or look at the graph, it is now a positive 0.2, and that is from 9 seconds all the way up to 12 seconds here. Sorry, I went a little bit past that. Then we can look and see from 12 seconds out to 17 seconds that we have a constant velocity, no slope. So we would drop down to here. And then finally, or not finally, two more here. Here we have a new slope at 17 seconds. And if we calculate that out, that actually jumps up to 0.4. And so now we are all the way up to 0.4, and we do that to 20 seconds. And then at 20 seconds on the graph, we go back to flat line there, so no slope, so no acceleration, like that. So negative 0.2, 0.2, 0, 0.4, back to 0 there. All right, now we got a horizontal projectile problem. So it says we're going to go off a table here. The table is 0.4 meters above the ground, and we're going to have the same constant velocity right here that we leave the table with. So that means we are leaving the table with a velocity of 0.8 meters per second there. And so the first thing that they ask us to do is find the time from when the cart leaves the table to it hits the floor. We should be really familiar with this by now. And so what we're going to use is the third equation, where delta y equals v0y times t plus 1/2 times the y acceleration of g times time squared. There is no initial velocity. Rearrange this equation to get time is the square root of 2 times the change in y over g. And now just plug in. Our change in y is negative 0.4 meters, and our acceleration is negative 10 meters per second squared. And when we work all of that out, we're going to get it's 0.28 seconds to hit the floor. And lastly, they say the horizontal distance that it lands from the edge of the track there, so this distance basically right there. Oops, sorry. I didn't realize I had that off the top of the screen there. So we're going to find this horizontal distance right here. A horizontal question is simply this equation, because we are not accelerating. You can think of that as the third equation with no acceleration. Our velocity, as we said, is the same one that we left the track with, which is 0.8 meters per second. Our time we just found there is 0.28 seconds. So you'll get roughly there 0.22 meters.